Welcome to this video. This is going to be a short video in which we're going to define the concept of continuity for complex functions. Now, the reason this video is going to be short is that this is extremely simple because it's completely and utterly analogous to the way that continuity is defined for a function from R2 to R2 in vector analysis. However, despite that, we will go over it separately here. So, let's say that we have a function f, which is a complex function, so it maps the complex numbers onto the complex numbers. The function f is said to be continuous at a point in the domain, and we'll call that point in the domain z0, so we'll have our picture. So here's the domain, and we'll take a point z0, and that will be being mapped on to a point in the codomain, which will be f of z0. So that's the function, mapping it there. So the function f is said to be continuous at this point z0 if the value of the function at z0, f of z0, is equal to the value of the limit of the function as z approaches z0. So this is the condition. So the actual value of the function evaluated at z0 needs to equal the limit as z approaches z0 of f of z. And if that is true, so if the point, the value that you map z0 onto is the same as the value that you would expect to map z0 onto by looking at the points surrounding it, which remember is what the limit means, then we say that the function f is continuous at z0. So I might just change colour. So this, if this is true, then we say f is continuous at z0. And if this is true for a whole region of the complex plane, so if we go back to our picture here, if we take a little section of the complex plane, we could call this region here maybe D. So if we have a whole area of the complex plane, and for every point in that area, so for all little z0 that is in this disk, if you like, here, this section of the complex plane, if it is true that the value of the function evaluated at all those points is equal to the value of the limit as the function approaches the point, then we would say that the function is continuous over D. And if it is true for every point in the complex plane, so if this condition is true for all z0 is an element of the complex plane, then we'd say that the function is continuous over the entire complex plane. So that's what it means for a function to be continuous. That's the strict definition. Let's now just explore a little bit what this means. And this is completely intuitive as long as you understand what the concept of a limit was. So remember, we discussed limits in the previous video in the playlist on complex analysis, and we saw how what a limit means is what do you expect the value of the function to be as you get closer and closer to z0. So we saw how what you're doing really is you're looking at all the points close to z0, in the neighbourhood, if you like, of z0, and you're looking at what do they get mapped onto in the codomain, and you're using that information to predict where you would predict the value of f of z0 to be. So that's what limit of a function really means. It's saying, look at the surrounding points, look at where they're being mapped onto. From this, where would you predict the point of interest, the central point, to be mapped onto? That's the concept of the limit. And all this definition of continuity is saying is that we want the actual value of the function at that point to be equal to what we would expect it to be. And this is completely intuitive because remember our example from the previous video, and I don't remember the specifics of the example from the previous video, but I can invent a very similar example. So let's go back to having white pen. So if we take, for instance, a nice simple function, and we'll often appeal to these functions in complex analysis because they're so easy to visualize. So if we take a nice linear function, so we'll take f of z is equal to z, and then we'll just add some fixed complex number on. So we could add, I don't remember what we added in the previous one because I made the video a long time ago, but let's add 2 plus I. So we're adding 2 to the real component and 1 to the imaginary component. So let's think of where that's going to take everything. So we know where the origin is going to go. So 0 is going to go to 2 plus I, so we'll map that on there. And from that translation, we can then see what is going to happen to everything else. It's all going to be shifted along horizontally by 2 and vertically by 1. So 1 is going to go to 3. In fact, I might just colour a few of these in. Oh, we could actually draw a little sort of square of points. So the points that I've highlighted there, we've got the origin, which is 0, we've got 1, we've got I, we've got 1 plus I. Where are all of those going to be carried to by this function? Well, we've already marked on where 0 is going to go. Here is where 1 is going to go. Here's where 1 plus I is going to go, and here's where I is going to go. So everything's going to be sort of shifted in that way on the complex plane. So that is a beautiful function. That is obviously continuous. It's clearly true that every point in the domain here is going to be mapped onto the point that you would expect it to be mapped onto. And from our intuitive concept of what it means for a function to be continuous, and I hope everyone watching this does have an intuitive concept of what it means for it to be continuous, it means that there's not any surprises in the function. Everything's just being beautifully stretched, if you like. In this case, it's not even being stretched, it's just being translated. But functions that are continuous, they don't sort of have any cuts or unexpected holes in them. Everything is beautifully continuous. All you've done is either translate it a little bit, maybe stretch out the points a little bit. So remember, everything's from here is being carried onto a point here, and so you can effectively imagine picking up the complex plane and maneuvering it over to the points where they're going to be. And in this case, we've just sort of picked it up and we haven't even stretched it at all. We've just maneuvered it, we've translated it, and that's a beautiful continuous maneuver, and that's why we intuitively describe this function as continuous. More complicated continuous complex functions might stretch everything out. So we could take a slightly more complicated complex function. We could take the complex function f of z is equal to 2 times z. And of course, what's that going to do? That's going to stretch everything. So we know what that's going to do to the and I'd better draw a separate picture for this, so let's get a bit more space. So we can draw this, so we'll have our domain here, we'll have our codomain here. So what's this going to do? So this is another nice linear function, a little bit more complicated than just adding a complex number on. We're now multiplying by a real number, which is simpler obviously than multiplying by a complex number. So everything in this case is going to be stretched. So 0, where is 0 going to go? 0, when we multiply it by 2, is going to stay as 0, so that's nice and simple. 1, where is 1 going to go in this case? 1, when we multiply it by 2, is going to go to 2, so we can see that it's being stretched out, and indeed, we know exactly what's going to happen to the real axis. Everything's just going to be multiplied by 2, so all the positive numbers are going to be stretched, so they're twice as far from 0 on the real line, and all the negative numbers again are going to be stretched in the opposite direction, going more negative, again, so they're twice the distance away from 0. Now let's think about an actual complex number, so let's go to I here. When we multiply it by 2, it's going to go to 2i, so we can then see that all of the numbers on the complex axis here, they're all going to be stretched in exactly the same way as you would stretch the real numbers, so they're all going to, all the positive imaginary numbers here are going to be stretched upwards here, and the negative ones are going to be stretched down here. What about one that's got a mixed component? Well, you know what's going to happen here. I plus 1 is just going to become 2i plus, 2 plus 2i. So it's going to end up stretched like this. So we can easily see that everything's just going to be stretched away from 0 so that it's twice as far away from 0. All the real and imaginary components are going to be multiplied by 2. So effectively here we're just stretching the whole complex plane out, but that's still a continuous maneuver. So intuitively this function is what we want to be deemed a continuous function. And indeed both of these functions are continuous. You can see that all the values that you're taking everything to is what you would predict it to be taken to by looking at all the points around it. Put another way, if you were to draw a little ball around a point here, that little ball would end up around that point over here. So if you were to actually rigorously work out the limits for where all of these points are being taken to, they would be being taken to the value. Intuitively, though, it's far better to work with intuition than rigor. Rigor is boring, intuition is beautiful. Intuitively, everything is going where you would expect it, and all the neighbouring points in the domain are still neighbouring points in the codomain. If we then take that ugly example that we had last time, so we started with a beautifully simple function, and then we said, okay, let's make it ugly. Let's take one point, so we might take the point up here, 2 plus 2i, and instead of sending it to what we would expect it to go to, and it should go to 4 plus 3i using this function, let's instead send it to something stupid like negative 3. So it's going to be negative 3 when z is equal to, and I apologise for drawing over my other picture, but never mind, 2 plus 2i. So for all the other complex numbers, it's going to be equal to this, the value of the function, but for this specific complex number, you're going to send it to negative 3. So this one is now going to go to over here somewhere where negative 3 is. That would then make this function discontinuous, because now if you were to take the limit of this function as z approaches 2 plus 2i, of course the value it should go to, the value you would be expecting it to go to by looking at all its neighbouring points, would be 4 plus 3i, whereas the value it's actually being sent to is negative 3. So at that point, the point 2 plus 2i, this function would be discontinuous. At all the other points of the complex plane, it would be continuous, because this condition would be true, but at that point, it would be discontinuous. Let's, just to end the video, go to one more complicated example, because we shouldn't just use the linear functions. We should go to some more fancy functions. So let's now take the function f of z is equal to z squared. So the simplest of the nonlinear polynomials. So let me remind you what this function does. So back to basic facts about complex numbers. When you multiply a complex number, or when you multiply two complex numbers, remember it's useful to remember that the argument modulus form, and we know that we multiply the modulus of the complex number and add the arguments. So I'll just draw a picture. So if you have two complex numbers, let's say z1 and z2, and you want to multiply them together, the third complex number that you will get is going to have arguments equal to the argument of z1 plus the argument of z2, and it's going to have modulus equal to the modulus of z1 times z2. So whatever the value is, which is z3, then the modulus of z3, which means the distance it is from z1, from 0, from the origin, is going to be equal to the modulus of z1 times the modulus of z2, and the argument of z3 is going to be equal to the argument of z1 plus the argument of z2. In terms of the picture, what that means is that you take the distance that they are, the length of this line connecting them to the origin, you multiply those two distances together, and that will give you the distance of the final one. And to find the angle that it's going to be at, you need to add the angle of z1 to the angle of z2, and that angle, remember, is the angle that it makes with the positive real axis. So you do this, you find that angle there, that's the argument, and you find the length of that line, that's the modulus. So z3 is going to be maybe somewhere up there, we can imagine, like that, because we've added those two angles together, and we can sort of see it's going to be maybe close to 90 degrees there, and we've multiplied those two moduluses together. And that's helpful when gaining intuition about this function z squared here, because when you square a function, that means you're going to effectively square the modulus, because you take the modulus of z, multiply it by itself, so you square the modulus, and then you add the angle to itself, so you double the angle. So that gives us a helpful intuition of what's going to happen. Let's, whoops, don't want to do this in red, let's go back to white. So, firstly, we know what's going to happen to, and then we need two. So let's have the domain and the codomain here. So we know what's going to happen to the whole of the positive real axis. They're just going to be carried to the same thing as they would be carried to back in basic real analysis, z squared, or x squared in real analysis. So 1, when you square it, is going to obviously give 1. The numbers bigger than 1 are then all going to become bigger, so 2 is going to go to 4, 3 is going to go to 9. The numbers smaller than 1, so between 0 and 1, they're all going to get smaller, so 0.5 will go to a quarter, etc. But they're all just going to be stretched smaller in this space. So the ones up here are going to be stretched outwards, the ones inside are going to be stretched downwards, and of course we know that 0 will be carried to 0. The negative numbers, what happens to all of them? In fact, we'll come back to the negative numbers because that's a little bit complicated because we know they all become positive, but it will make more sense to see that in a moment when we've looked at what happens to the imaginary axis. So let's now go up the imaginary axis, have a look at what happens to I. Now, of course, you know what I squared is, but let's think about it in terms of modulus argument. Its modulus is 1. When we square that, it remains as 1. So it's going to remain on the circle of radius 1. So I could draw the circle of radius 1 here. So it's going to remain somewhere on there. Now what has to change is its argument has to change. We have to double its argument. Its argument is 90 degrees, or pi by 2 radians, so its argument is going to become 180 degrees, pi radians, and therefore it's going to end up here on -1. So that worked fantastically well. So I comes here, and in fact, whilst we've got the unit circle there, all the complex numbers of modulus 1, they're actually quite a good set to study because they obviously, their modulus isn't going to change when we square them, but their argument is going to double, so they're all going to get rotated on this circle. So if we think what happens to -1 now, it's got an argument of pi radians, so when we double it, it's going to go to 2 pi radians. So it's going to end up back here all the way on +1, which is excellent. We know that -1 squared is 1, so that's beautifully obeying what basic fact. And you can see that this entire portion up here, the part of the complex plane with a positive imaginary component, all of that is actually going to take up the whole complex plane. So this function is not going to be 1 to 1. It's going to be 2 to 1. There's going to, for every point in the codomain, there's going to be 2 points in the domain that are being mapped onto it. So in fact, to simplify this, let's imagine taking off the negative part of the complex plane, the part with the negative imaginary numbers. So take this bit out, keep the real axis, keep the positive real axis, get rid of the negative real axis for a moment, because that complicates matters, because all of the negative real axis is being mapped onto the same thing as the positive real axis. So just to try and make the function 1 to 1 for a moment, I've taken away all of this bit, and I've taken away the negative real axis as well. We've kept the positive real axis, and we've kept all of this bit up here. Think what happens here. Well, again, look at the unit circle of complex numbers here. These are going to be spaced out. We know that as we get closer and closer to -1, that one is going to come all the way to 1. We've got rid of that because we don't want to quite get all the way back onto the real axis because we're trying to think 1 to 1. But all of these ones here that are just short of being on the having an argument of 180 degrees, they're going to be mapped right round to here, and you can see that this function is effectively twisting it right round. So I'm going to get another colour to highlight. This bit here of the unit circle that I'm highlighting in yellow, it's going to be stretched out and become an entire full unit circle in the domain. And then all the other complex numbers that don't have modulus equal to 1, they're going to be carried to double their argument as well. So if we draw like a line here, where's that going to go? We can say that this is pi by 4 radians, 45 degrees. You can see that that's going to become pi by 2 radians. That's going to be carried to here. Now, all the points that don't have modulus 1, their modulus is going to change. So they're either going to be stretched outwards if their modulus is greater than 1, or stretched inwards if their modulus is less than 1, the same as the real axis is stretched in that way. So hopefully that sort of starts to paint a picture of what this function is doing. It's twisting everything round whilst stretching it out, or if its modulus is less than 1, stretching it in. The only point that remains where it is 0 and 1. Well, there's 2 points. 0 and 1 remain where they are. Those are the only points that remain where they are. Everything else is going to be twisted round and stretched. and this function is not 1-to-1, it's 2-to-1, because this portion here of the complex plane where the imaginary component is positive, that's going to be stretched onto the entire complex plane in the codomain. And likewise, this bit here, if we look at where all of these bits go, let's take a concrete example. So let's take this one here, where we have modulus 1, and then argument would be equal to pi plus pi by 4, so that would be 5 pi by 4. So I was trying to go for this angle here being 45 degrees. If we add that onto pi here, then the full argument is 5 pi by 4. If you think where that's going to go, its modulus is going to remain 1, because its modulus was 1 to begin with, so when we square it, it equals 1. But its argument is going to double, so it's going to go to 10 pi by 4, which is equal to 2 pi plus pi by 2. 2 pi is equal to the whole thing, that's 360, so we're only interested then in the pi by 2 bit, so it will come up to here. It's going to be equal to I when we square it, so it goes right round there. And likewise, all of these points here, they're going to be stretched out, and they're going to again cover the whole of the complex plane if you think about it, because this one has already been, if you think where -1 went, it was already stretched around to here. These ones are then going to be stretched onto this bit. The bits in this quadrant are then going to be stretched back all the way around onto the negative part of the complex plane. So to make this absolutely crystal clear, this quadrant of the complex plane, this is going to be stretched onto this whole half of the complex plane here. This bit is going to fill all of this half. This one again is going to fill all of this half, and this one is going to fill all of this half. And the way it's working is it's twisting round twice, if you like. It twists it right round so that it covers the complex plane twice. So it's this tornado stretching function. Now, proving rigorously that the limit of the function at every point is equal to the value of the function itself is a bit boring. It's not that much fun, but intuitively, I hope you can see that every point in this function, because it's a stretching and twisting function, it is intuitively continuous. You're not cutting anywhere, you're not breaking anything, and even at this bit here, you might wonder whether it's continuous on this line, but if you think about how it's going to end up stretching it, even though it's going to pick this edge here, if you like, up, even when you think about this function, even though to think about this function you have to imagine cutting here and then grabbing this free end and twisting it right round and stretching it a whole time round and then bringing it back. When you bring it back, you can imagine connecting it back up, because these points, when you look at where they're going to end up, they do actually end up near where you would expect them looking at the real line. So even though to imagine this function you have to imagine snipping here and then writhing the whole thing round, when you actually bring it back, it does actually connect back up. You can imagine stitching it back together with the original thing, and then it does actually all work out so that it's kind of still continuous. So I hope you intuitively see that this function is continuous, and that if you were to try and prove this rigorously, you would find that all the points are being carried to, are actually going to where you would expect them to go if you were looking at all their neighbours. So points that are neighbours in the domain are still neighbours in the codomain, because you haven't snipped anything, you haven't put any holes in anything, you've just writhed things round, you've twisted and stretched, and that is the intuitive concept of continuity. So I'm not going to rigorously prove that this function is continuous, but I hope intuitively it is obvious that it is continuous, and that this rigorous definition is just capturing that intuitive concept. Fundamentally, all this is saying is that points that are neighbouring next to one another, topological neighbours if you like, in the domain are still neighbours in the codomain. I.e., if you look at the neighbours and try and predict where the central point should be, it is actually going to that point. Thank you for watching this video.